Welcome to Breadboarding. In the previous video we went through Windows 1, 2 and 3 and we're looking at the differences, particularly in the screen furniture, the icons and the control menus and things. And these were all screenshots from the Breadboard PC. So this is video 65 in the Breadboard 8088 PC series, and this is project completed. So I've pretty much completed everything that I set out to do. There was a few things that I haven't done and I'll explain the reasons for that in a few minutes. But first of all, let's take a quick look at the board and just familiarise you with all of the various sections we've been developing. I started, the first video for this was published in December 2023, so it's just over 13 months I've been working on this project. So this is the final state of the Breadboard PC version 1. I'll just take you through some of the key things here. It's still a little bit messy because I've got the logic analyzers here hooked in quite a few places, and one of the reasons why I've left these here is that in a number of occasions I've unplugged the logic analyzers to do videos, and then I've managed to disconnect a wire somewhere and it's taken me another half a day or so to actually work out what's gone on. So I'm leaving the logic analyzers in there. It makes it a little bit more messy, but apologies for that. What I have got plans to do in the next project is to make using the logic analyzer a lot simpler. So down here we've got our Intel 8088 CPU here, and this is a 16-bit CPU, but it talks to the outside world through 8 bits, and you can just about see the 8 data bus bits there. We've then got the system clocks are underneath here, so the main system clock and a lot of the timing and reset circuitries underneath here. Then we've got buffers from the CPU to the rest of the computer over here. The EPROM here, so the read-only memory, this contains the BIOS and the system monitor, which I'll talk about in a minute. And we've also got 512K of RAM here, so this is static RAM, we're not using dynamic RAM. Now at the top of the board up here, we've got the DMA controller and all its supporting logic. Now the DMA controller I'll be talking about in a minute, but the DMA caused an awful lot of trouble, and in fact the computer as it stands at the moment is not using DMA. We've also got interrupt controllers, system timer, and at the very top here we've got the power on self-test ports and a couple of the other ports which are needed for the base PC compatibility. Over on the left here we've got a floppy disk controller which is connected to this 3.5-inch high density 1.4 megabyte floppy disk. There's also the PS2 keyboard and mouse controller, so we've got a PS2 keyboard and a PS2 mouse plugged in here. And then there's also the modern SATA hard disk plugged into a SATA to IDE converter, and then this is then plugged in down the bottom here. The IDE controller is actually underneath here, underneath the display here, 7-segment display here. Now the base design of this, we're using Busboard Prototype Systems breadboards. So these are high quality breadboards. They cost about £7-8 each, probably about $10 each. I get these from Mouser and I tend to buy them in packs of 10, so they tend to be a bit cheaper like that. We've also been using the power strips as bus connectors, so you'll see that the address bus and the data bus and some of the control bus have been using these as well. Now these actually, I was in two minds whether to use this. These have actually worked fairly well. However, there are a few problems with using them. In particular, the problem tends to be because the connectors are in twos, and so it makes it a bit easier for them to become pulled out. And I've also been using these breadboard buddies. So these are power connectors from Tindy. So Hack Modular, I think, produces these, and these are quite useful in that they just fit in on the ends of the boards and actually can tie up to 3 boards together from a power point of view. One of the big issues with breadboard projects like this is the power distribution, and we'll be talking about that in a minute. But up the top right hand corner here you can see this is where I've got the power distribution block, and there's cables going all around the place to actually provide power to the rest of the board. Now over on the left hand side here, the first video card we built was a monochrome display adapter compatible one. Now this is a bit simpler than the later one we did in that there is a large RAM chip here, and this is a dual port RAM chip. So this has data and address lines on both sides of the chip, so we can hook it into the rest of the computer and also into the cathode ray tube controller that runs the video card here, and we'll never actually fight over access to the RAM. The only problem is that these chips are now no longer made, and they've probably doubled in price in the last sort of 2 years, and they're only in 4K sizes, so you'd need a lot of these expensive chips to actually make any sort of substantial video card using graphics. So the monochrome display adapter is the 4 boards around here. Down the bottom here we've got the real-time clock, so this has a CMOS backup battery, so the clock actually does run when the computer's turned off. And if we just take the LED display away, the IDE cable, and there's a very simple IDE controller. It's basically a couple of buffers is really all an IDE controller is. Most of the intelligence is actually in the drive itself up there. Now, in addition to the 7-segment display here, so you can see this is Nanocomp 8088 version 5, I think this is. There's also a keypad like this, and this was a carryover from the Nanocomp 6809 project that I did probably about 2-3 years ago, and this is just based on VeroBoard strip board and different connectors and things. But that keypad has been very useful, and I'll talk about the system monitor, and this is basically what runs up before we actually get to the BIOS. So in fact the way how I've configured this is with the monitor I can actually inspect memory, run test programs and things like that before I try and load up the BIOS and load up MS-DOS, etc. And then all I do is press B on the keypad there to actually boot the BIOS. And down the bottom here, this is parallel interface and a serial port. Now these are actually using the original Motorola chips that I used on the Nanocomp, and the main reason for that was really that the code in the monitor was designed to work with these chips rather than the Intel variants, and that's one of the things I may look at changing in future projects. You can see down here we've got little mini voltmeters. There are a number of these mini voltmeters around the board, and this is because sometimes you'll find that the voltage can drop quite a lot. In fact, on one of the early versions of the 6809 Nanocomp, I found that the voltage in one corner of the board was about 3.5 volts, and that will definitely cause you problems. Now this monstrosity over on the right hand side here, this is the full CGA IBM PC compatible video controller. So this is completely compatible through the memory map and through the registers. It does actually produce the VGA output so that it actually hook into all the various video capture devices I've got. So it isn't actually producing CGA output, but it's not that easy to actually integrate CGA output into video capture. I've also used this with external monitors as well, which obviously I don't have a CGA monitor, so that's not an option. Now the only issue with this is that the timing on this is obviously different from the original CGA. So some of the 88 MPH type demoware won't probably work very happily on here because the timing is different from the original CGA card. So that's the basic breadboard PC. What I'm going to do now is to go through some of the things that work well and also some of the problems and things that I've had and things that I'd actually like to do better in the future. So what I'm going to do is to boot this up, and you'll actually see on the top right hand side here that as we boot it up, the BIOS will come up in the right hand side here. So this is the XI8088 BIOS by Sergei Kiselev. This was a great project. Sergei's got some fantastic resources on his GitHub, including PCB designs for 88 style PCs. So you can see that this is skipped the A drive and has actually booted up into DOS. We'll just run this up into Windows 3. Now Windows 3 does take a while to run up on 8088 PCs, so I'll just leave that in the background whilst we actually carry on. So I'm first of all going to go through the plan that I had from the very first video. So this is my original high-level plan from the video number 1 in December 2023. And the vast majority of the plan being able to stick to. There's a few minor changes in the order and things along the way. I was originally thinking I was going to have to use the Intel hex file format, but in fact the utilities I've been using all support the Motorola S record format, or SREC, and this was actually easier to use because the monitor already supported it. And there have been a few things towards the later end So the multicolour colour graphics array, which was a little known graphics controller which appeared in some of the lower end PS2 machines, so I think it was the PS2 model 25 and 30, the drivers for that only support 286 processors upwards, so I decided not to do that at this point in time. The serial point-to-point tunneling protocol networking, I thought I was, due to some of the stability issues I was having running higher versions of Windows, certainly Windows 3, then I figured that it was probably better to stabilize the system before doing too much here. We managed to get the PS2 mouse running Windows 1 and 2 and also Windows 3, but the network adapter, I do have a surface mount chip for doing this, and I would need to acquire a similar surface mount sound card. Decided to defer doing those until such time as I've actually reworked the board and made it more stable. So this is the completed high-level plan. So these are all the bits as we've gone through it over time, and all I've done is I've resurrected some of these ones at the end here. So these are the ones that we haven't done, but everything else we've actually gone through. And also along the way, Microsoft released the source code for MS-DOS 4, so we also went off and built our own version of MS-DOS 4.0.1, and that was allowing me to do a certain amount of debugging of some of the floppy disk and DMA issues. So let's have a look first of all what went well. So the key thing, the PC worked and was able to run MS-DOS, Windows 1, 2 and 3. This is MS-DOS 3. I was able to get PC-DOS 2.1 working in the early stages, and I have been able to get MS-DOS 4, 5 running as well. However, I've stuck with 3.30 because that is compatible with these early versions of Windows. We then got Windows 1 running, Windows 2 and Windows 3. There are a few artifacts that you get on the screen with Windows 3. There must be something with the video card anti-snow changes that I did which don't quite work in Windows 3. Then the BIOS was based on Sergei Kislev's XI8088 BIOS. This is excellent bit of software. It was easy to understand and to tweak, and also included enhancements to work with PS2 keyboard controllers and mice and the real-time clock and CMOS configuration. So you can see here, press F1 to run the BIOS setup, and you can also see down here that it's detected the adapter type as being CGA. There was a link on the keyboard controller that switches between CGA and MDA, similar to what the Compact Desk Pro did. You can see that we've got the mouse has been detected here. Don't have any serial ports or parallel ports. We've got a 1.44 megabyte floppy disk drive, or more accurately a 1440 kilobyte drive. It's slightly different capacity. Total conventional RAM is 512K, although because we needed to include support for the extended BIOS data area for the PS2 mouse support, then that takes the 1K region at the top of RAM for that. So the available conventional RAM is 512K, and this has also found the BIOS extension at the bottom of the EPROM, and that's the XTIDE BIOS, which is actually used to boot the hard disk and provides all the hard disk BIOS routines. So the monochrome display adapter that was built in the early stages of the project, as I said previously, it used a dual port RAM, which made the design of this much easier and meant that we didn't have any video interference whilst the PC was updating the data. It is 100% register compatible, although the output is actually VGA compatible, so the timing won't be completely 100% compatible, but from a programming point of view, it will be 100% compatible. And a little known fact is that the monochrome display adapter was also capable of generating colour as well. So this is actually the colour output produced from this. Then the CGA graphics adapter, the colour graphics adapter, this was a more complicated part of the project and has taken up a good chunk of the last couple of months. So although the video mode is very similar, you'll see the font for the character set isn't quite as nice. It's only an 8x8, whereas the previous one was actually based on 16x8. But this was made more complicated by needing at least 16K of RAM, so I couldn't use the dual port memory, and also has a variety of video modes. So this is the 80x25, then we've got the 40x25, then this is the 640x200 high-res graphics mode in 2 colours, and that is also what is used by Windows 1, 2 and 3, which is why you'll see with CGA graphics you'll only get black and white in Windows. And again, this is 100% PC register compatible. It does generate VGA output. So again, some of the demoware applications like 8088, MPH and things like that won't really work very well on it because the timing's quite different. So I didn't really have any power related reliability issues. So these are photos of the bench power supply I use. In the early stages, you can use a USB power supply, certainly up to about 1 or 2 amps. You could probably use a USB power supply. But you'll see here that the voltage is actually set at 5.4 volts. The current limit is actually set at 5 amps. And when it turns on, it settles down at about 4.1 amps, but it does spike at about 4.7 amps as the SATA disk and the floppy disk drives spin up. Now, I've covered this in the breadboarding tips videos in the past, but making sure that a large breadboard project, so this breadboard project has 25 breadboards in it, you need to make sure that you've got good power distribution. So this is the power distribution block that I showed in the beginning, which actually has wires going out to connectors such as this one here. So these connectors I've made, which are soldered and have generally about 3 pins on each power rail to ensure good connections. I did try using thicker wire for these, but the problem I found with thicker wire is these connectors used to then lift out. So in fact, there's a trade-off between using thicker, lower resistance wire and this hookup wire. I found this to be more reliable. And there's also some places where I have to join boards together from the ends where there aren't these sort of lugs, and so I made these sort of connectors again for that. And you can see here, these are the mini voltmeters that I've got located in a number of positions. I tend to put them in the far corner of the board so that you can actually see if there's a voltage problem. Generally, you'll be all right if these are above 4.5 volts. There were some of the early projects I did on the 6809. My video card had about 3.6 volts in one corner, so that was definitely causing problems. So I'd recommend trying to get these type of little power meters. They are £1 each from my local supplier, Bitsbox, I use in the UK, and they're definitely worthwhile putting in certain locations around the board so you can spot power problems before they bite you. Now, this was a tip that somebody commented on one of my videos, sort of about a third of the way through the series. I use quite a few of these sort of Dupont ribbon cables, but I was using them with the single sort of connectors on the end, and they get quite fiddly to plug in, and also then the odd one can actually become unplugged quite easily. And the commenter suggested that you can remove these quite easily off the end, and I have got a video showing where that was done, and then you just clip these ends into one of these shells. Now, I tend to use the 8-way shells most of the time, but I have got 2, 3, 5, sort of 6, 8, 10 and I think 12-way shells as well. So it means that you can actually make the connector so that it actually will plug in, and it's a lot easier to see if this connector has start to become disconnected when you've got sort of 8 or more of them in rather than just 1 or 2 at a time. Now, the Nanocomp monitor, I've shown you display and the keypad already. So the keypad was almost identical design from the original Nanocomp 6809 project. But the Nanocomp monitor, I migrated from the 6809 assembly language over into the 8086 assembly language. I was going to rewrite it in C, but it actually turned out to be easier just to convert the assembly language. And the keypad had a number of functions. So we've got our hexadecimal 0 to F, and some of these are also used for commands. And then we've got the load from serial port, save to serial port, and this uses the S record text format, which is a Motorola format. Continue will continue from an interrupt or an abort. Go will actually execute program at a given 4 hex digit address. Reset is wired into the hard reset line. Abort is connected to non-maskable interrupt. On the original IBM PC PCXT, then the non-maskable interrupt was used for parity checking of the RAM. But since we're not using parity, then the non-maskable interrupt actually allows the monitor to abort where you are, and it will then actually show the registers on the display. M is used to inspect and set memory. R shows registers, and I is just sort of to increment between memory locations. Now, I had to extend the monitor a little bit because the 8086 and 8088 can address up to 1 megabyte of memory, but it only has 16 bits which is 64K. So the 8086 has a segmented memory model, and so what I found I needed is to actually have a couple of extra commands to be able to set the extra segment. So the extra segment is generally used for accessing the memory and for saving and loading, and then the code segment is used to actually set the higher part of the address used for the go command. So the other thing that was very useful with the power on self-test port. Now the original PC and PCXT I don't believe had a power on self-test port, or post port as they're known, although you could buy ISOBUS cards that would actually provide that facility. But the XI8088 PC design of Sergei Kislev included this, and so I've included it. It was actually very useful, and you can use it for plugging into the logic analyzer. The original power on self-test boards would tend to have like an LED display to show you what the last code was, or sometimes it would actually cycle through a couple of codes if there were multiple bytes being provided. But by plugging this into a logic analyzer, then you can actually see the whole full history of the power on self-test codes. So you can see here with the logic analyzer with the D0 to D7 on the power on self-test port, it's triggered on the chip select for the power on self-test port, and I've also got some of the mouse data here, the clock and the PS2 clock and PS2 mouse data here, and you can see here it's decoded. If you expand this, you can see that these are the codes that the BIOS generates as it goes through, and if there was a failure then you'd be able to tell approximately where things had failed based on the code that you had there. And then in the BIOS was actually an error number table, so this include file actually has all the various error codes. So based on what the last number you saw was, you could actually read it off here, and if there were RAM failures then you'd get a code here that would indicate whereabouts the RAM was failing. So low RAM would be the bottom 32K of RAM, for example. So what could be done better? So there were quite a few issues I had over time, but by far the biggest one probably is DMA. So what is DMA? For those of you who may not have seen some of the videos from earlier on in the series about direct memory access. So this was dedicated hardware for transferring data bytes between memory and peripherals, generally floppy disks and perhaps some of the early hard disks. Now the Intel 8237 DMA controller was used in the original PC and PCXT. It was already quite an old part, so it'd been around for a number of years, and there were better parts available, but I suspect IBM were trying to build this as quickly and as cheaply as possible. Even in 1981 this was kind of like a legacy part, but you'll find that in fact even the PCs you use today will probably include this emulated, in that the chipsets from the 486 upwards tend to include the DMA controller emulated in them, and this would still probably be running at about 5 megahertz, which is about the original PC speed. Now the PCXT ISOBUS DMA is different from later DMA. So DMA used in PCI and PCI Express is quite different and quite a lot faster. There was a reference here in this document, and it included a comparison of clock cycles per byte for the original 4.77 megahertz PC versus a DMA. So you can see that the original PC to process a byte was 39 cycles, but for DMA was only 10 cycles. So you could see that for the original 4.77 megahertz PC it made sense in that it was about 4 times faster. The only problem is about a few years later, when the 286, 10 megahertz 286s came out, then this was about 5 times faster than the basic 8088. So in actual fact, programmed I/O, or the CPU accessing the peripherals, was actually faster than DMA, and DMAs had to be stuck at around 5 megahertz for backward compatibility for about the last 40 odd years. Now IBM introduced the PC Junior as a sort of a low-end sort of consumer PC, and this didn't have DMA. Now the Wikipedia article says the BIOS routines for handling floppy access were different and more complex than those on the PC. Well, I don't think that's actually right, in that having done this, the changes needed to actually disable the DMA and to enable the programmed I/O was only a few hundred lines in the BIOS. And the original Tandy 1000, they omitted DMA just because PC Junior didn't have it. I think later Tandy versions did actually have DMA. So DMA wasted a lot of time getting the floppy disk controller working. Now the PC BIOS floppy disk interrupts rely on DMA for actually reading and writing the data to the floppy disk controller. And I went through multiple DMA controller chips just because they would work for a few tens of K when accessing the floppy disk, but then would start to return the data bytes in the wrong order for no apparent reason. I tried about 4 different chips. So 2 original ones, which I got from around the sort of late 70s, early 80s, and I tried some more modern versions as well. I could get PC-DOS 2.1 would boot some of the time, but that was because the total code size needed to boot the operating system was only about 44K. When I tried the other DOS versions, they were slightly larger, and it seemed to go wrong sometime between 44K and 77K upwards. So I looked at the PC Junior BIOS and had a look at how to do it, and actually it wasn't so bad. It probably took about 3 or 4 days to get it all working. So really makes the comment on the previous screen look kind of incorrect. So the programmed I/O basically uses the CPU to poll the status of the floppy disk controller until it has a byte available to read. The only problem I ran into is the PC Junior used programmed I/O, but it only had a 360K floppy disks. Now these work at a data rate of about 250 kilobits per second, but the high density 1.44 megabyte floppy that I'm using works at twice the speed, so it's about 500 kilobits per second. And the problem I was running into is that I just didn't quite have enough speed with the 4.77 megahertz CPU to actually service the floppy disk controller without missing any data. What I did find that if I overclocked the base clock from 14.3 megahertz, which is kind of tied to the CGA video signal, to 16 megahertz, so this means that the CPU is going to be working a little bit above its maximum 5 megahertz in the spec sheet, but slightly overclocked, and that actually gave me a cycle time which was about 22 nanoseconds quicker, and that actually allowed the CPU to be able to read data from the floppy disk without any errors. So there's only about 500 lines of the floppy disk controller BIOS which are different. There's quite a lot of lines which are just commented out from the DMA. It's probably about 300 new lines you need for servicing the reading and the writing, but it's certainly a lot simpler than people might have thought. And looking at the section of the schematic where the DMA controller is actually located, all these crosses indicate either where the whole chip can be removed or where part of the use of the chip is actually probably reduced. So where there's a PLD here, programmable logic device, then probably we've freed up a number of the pins. So you'll see here that not using DMA frees 1, 2, 3, 4 chips plus probably another 1.5 of these other ones here. So it will simplify the chip count quite a bit and actually will probably work a lot more reliably. Now the other bit that at the time I remember talking about this in a video where theoretically the ALS chips that I was using had a fan out of about 40, so an output from one of these chips should be able to feed about 40 inputs. However, I did find as I was doing the DMA controller that I actually piggybacked another buffer on top of the base buffer here to give it a bit more oomph, because I thought that might have been one of the problems. And if we actually look at the oscilloscope output from the CPU, so there's a line, this is a feed taken from one of these pins and a bus pin coming from over on the left hand side here, you can see there is a bit more interference on the bus, and in particular this one over on the right hand side here. I'm not quite sure what's going on here, but this might indicate where the data on the bus may not be quite as good as what's coming out of the CPU. The data on the top here is from a completely different time period from the data on the bottom, so not from the same time. Perhaps if I got the 2 probes, we show the comparison, but it does indicate that perhaps there might be some issues here. And you can see down the bottom here in particular that there's not very much interference there. It's certainly well below the sort of 2.2 high voltage level, but along here it's probably getting a little higher, and this bit here and the slope here might indicate that there could be some potential problems there. So this is a screenshot from the Compact Desk Pro bus diagram, and you can see that there's actually pull-up resistors on a number of the bus connections here. I haven't gone through and checked what the pins are, but there's probably that these are primarily the data bus buffers and perhaps some of the control bus signals. So this has about an 8.2k resistor pull-up to 5 volts on those bus rails, and that is probably being done to reduce some of the reflections that you might get going backwards and forwards and interference. And the IBM PS2 Model 80 this is the similar sort of area. It did use a different bus architecture, micro-channel architecture, but you can see that there's also pull-up resistors on a number of these things as well. So I showed earlier the power rails that are used for the buses, and you can see here that there are a number of the connectors plugging in here. Now, because the power rails are in twos, you can't use an 8-way sort of bus connection here. You have to use 2-way ones. Originally, when I was using individual connectors, it was even worse, but the 2-way connectors are better, but still not perfect. And you can see here that down the right hand side here, you can see that the connector's just lifted out slightly. Now that's not enough to cause a problem, but it just indicates that these will lift out over time. And this other one on this side, you can see this one's probably lifted out a bit further. So I was always having to go around and just reseat these things from time to time. So I wanted to find a better way of using these buses really for doing the address, data and control bus signals. And also after the tip, using these Dupont cables and the 8-way connectors. So you can see here that there's a 8-way connection on the CGA card between 2 bits here. In hindsight, as I was pulling the 6809 project apart, as I was actually pulling these types of wires out on the right here between things, it became clear these are quite sturdy and won't come loose at all. And so I think perhaps in hindsight, I overused these Dupont cables. It was a lot quicker than cutting all these wires, but I think the board probably would look a bit better and be easier, would actually be more reliable if I hadn't have used quite so many of these Dupont cables, certainly for the short hops. For longer hops going across several inches, 4 or 5 or more inches, still makes perfect sense. But for these short sort of runs here, probably shouldn't use Dupont cables quite as much as I did. Then this was quite an interesting issue. The real-time clock keeps time when the PC's powered off. So it'll actually maintain time over 24 hours, from one day to the next. But when the PC is actually running, the clock actually runs fast. And say over a 5-minute period, the PC clock might show 6 or 7 minutes. So I was a bit confused about this, but as I looked into the data sheet, if we look at the data sheet for the real-time clock that we use, you can see that the 2 crystal pins here on pin 2 and pin 3 are right next to the data bus pins. You can also see here this is the 3 volts battery power. It keeps the CMOS memory contents and runs the clock whilst the PC is off. And in the data sheet as well, it actually says if you're doing a PCB for this, then you need to design your PCB in such a way that these 2 crystal pins are actually shielded from the data bus. And in fact, it's a little confusing here in that they've actually got this sort of cut here. So effectively what they're showing here is this pin and this pin here in red. Now, if I was designing a chip, I think I might have perhaps put the clock completely far away from where the data bus was, but I guess they needed to maintain compatibility. Now, what you can see here is the oscilloscope of the clock signal for pin 3 when the battery is providing the power is absolutely fine, nice and clean. But when the power's on, then it's obvious that the data bus is actually interfering with the clock here. Now, it wasn't helped that I didn't have data bus buffering for the real-time clock here, so this was connected up to the main bus, and so if I'd included data bus buffer here, then this would have only had data bus information when accessing this chip, so it wouldn't have been a bigger deal. But certainly it's something you need to look into and need to consider if you're doing this yourself. What I was thinking of doing is perhaps bending these 2 pins out, soldering the crystal to the pins directly, and perhaps including some shielding from the other data there. Now, as I was installing Windows, I managed to install Windows 1.0 and 2.0 okay, but when I came to install Windows 3, I did end up getting some hard drive corruption issues. So the file allocation table would get corrupted, and when I did check disk, then a lot of the directory entries and things were wiped out. And in the end, I ended up using some old PowerQuest drive image software to image the disk before I actually installed Windows 3. And I was able to get it working in the end, but it required re-imaging the disk a number of times. And afterwards, I did actually run, there's this disk test utility that is on this GitHub URL down the bottom here, and there's a wiki about it as well. And this was apparently developed to help test the XT IDE project, which is the design we've used for the IDE disk controller, and it actually uses a 4 megabyte test file with lots of different patterns. And you can see here that the ticks are where things have worked okay, but there are some exclamation marks here. And if you actually go on to the next page, you can see that when writing these sort of alternating patterns, so A's and 5s are like alternating 1s and 0s, and you can see that some of these patterns are actually coming up with problems. So I haven't gone into too much detail about that until I've actually sorted out the data bus buffering. Then I'm not going to worry too much about it, but there are obviously some problems when stressing the disk out at high data rates. I mean, this was obviously 4 megabytes, which is way bigger than any of the files that Windows or DOS are accessing. So certainly something, if you come to rebuild this, I will try and run this media test again and to get it so it's actually running cleanly. Now, another issue I ran into, I only really found out about this when I was actually testing the floppy disk controller. So the floppy disk controller that we're using comes in 2 packages. There's the PLCC, so this is sort of like the flat pack version, and then there's the breadboard friendly dip version. Now, at the time I didn't realise, but in fact the 40 pin version doesn't have quite enough pins to have the data change enable and the data change pins here. The issue here is that with a 1.44 megabyte high density floppy, then generally this is enabled with disk change functionality, and generally the BIOS will actually check to see whether the disk has changed, and there is a bit 7 on reading the status of this that the PLCC version of the floppy disk controller will actually provide that status. And so what I need to do in the future revision of the project, I probably need to do some sort of logic. You'll see here the red here is the dip pin. So on these particular 2 pins we don't have a pin there. So I need to work out a way of actually providing the disk change bit 7 when reading the LDCR port on this particular one. And at the moment the BIOS I've just hacked to indicate that the disk hasn't changed, and it's one of the reasons why I haven't actually used the floppy disk other than sort of for booting and loading software as a kind of a one-off. I haven't sort of done lots of disk swapping and things like that. So what next? So that's pretty much what I wanted to cover. It's been an interesting sort of 13 months. I started out having used PCs and programmed PCs for many years, and I know a fair bit about the hardware, but now I know the intimate details of exactly how everything works, or doesn't, as the case may be. So let me know in the comments below what particular areas you'd be interested in. I was thinking initially I'm just going to revisit the breadboarding tips. So I've done a couple of videos on tips on using breadboards in projects, so I was actually going to revisit those and update them a bit. I was also thinking, I am aware that not everybody has done electronics before, so I was thinking of perhaps doing some short tutorials for digital electronics for retro computers. So in particular covering all of the sort of issues with TTL and 5 volts and all sort of timing issues and the different types of chips that we've been using here. It's not designed to be a sort of replacement of a university sort of electronics course, but all of the useful information that I've come across needing to when doing retro computer projects. Also part of that, probably the programmable logic devices. What I wish I'd known about 3 years ago when using these. They're fantastic chips. They reduce the chip count quite significantly, but you do need to be aware of the limitations of them and some of the problems. And what I have been thinking about doing is simplifying the breadboard PC design, doing a version 2. I have actually got a modern C88, so this was bought from Mouser in the last sort of 6 months or so, and there are a number of the other parts which are still available to be bought as kind of new parts rather than from eBay. The Breadboard PC version 1 used legacy 1980s parts where practical. Sometimes it was late 80s, early 90s for like the PS2 keyboard controller, but they were basically parts from 30 odd years ago. I'm certainly going to remove DMA and only use programmed I/O, and I was thinking of using a strip board with the 0.1 inch headers for doing the bus connections, and I think that would be more reliable than the 2-way sort of power connectors that I've been using up to now. And I think that will also allow permanent connections for the data address and control buses for logic analyzer. So probably leave some cables plugged in there that I can just hook the logic analyzers into, and it wouldn't disrupt things quite so much. So that's it. Took one video longer than I thought it would be. Apologies if this is a bit longer. Than I would try and stick to about 20-25 minutes where possible, but I didn't really want to split this into another couple of videos. Thanks for watching the whole series. If you do want to catch up, there is a playlist which will take you from video 1 all the way up to this video, should you want to. I do recommend that you probably speed them up at about 1.5 times and put subtitles on, and hopefully you'll be able to get through them a bit quicker that way. But thanks for watching. If you don't want to miss out on future videos, whether it be the breadboarding tips, any tutorials, or the version 2 simplified breadboard PC design, if you could hit subscribe, and if you found the content interesting and useful, please hit like. It just helps to make the videos available to more people through YouTube. Thanks for watching.